Welcome back, physics enthusiasts. I'm Swati, and today's lecture is on important derivations. In this lecture, I try to cover four chapters: magnetism and alternating current, then electromagnetic induction, electromagnetic waves. I'm taking these four chapters because they're very small. They don't have that much of derivation. First, we talked about magnetism. Then, this chapter has more. Uh, it's more conceptual. I think numericals and concept based questions could be taken from this chapter. So you can focus on the properties of electromagnet, paramagnet, diamagnet, the susceptibility, dielectric constants, how they behave in magnetic field and everything. Plus bar magnet behave as a solenoid, and some terminology of magnetic bar magnet, the magnetic dipole and stuff. So there are very small relations and stuff. I don't think there are any such important derivation from the chapter magnetism. If I talked about electromagnetic induction, then again from this chapter, it's not that big chapter. It also has major conceptual and numerical questions. One or two derivations are there, like motional EMF, you can understand, then mutual inductance, then self inductance of a solenoid. That's it, and energy in an inductor. That's it. So next is alternating current. Alternating current have many relations. So numerically, it's a very good chapter, and in this we can understand the power laws derivation and impedance, resonance conditions, and that stuff. And from electromagnetic wave, again there is no any such derivation from this chapter, because this chapter you only have to remember the displacement current, the instantaneous equation of electric and magnetic field, how they are related, and then that spectrum. That spectrum is very important. The uses, you have to learn the frequencies, wavelength, and everything of the rays. And yeah, so these four chapters are more conceptual based, so you can revise the concepts, numericals, and everything from these four chapters. And then we can move to optics, because there are a lot of derivations from those four chapters. Those two chapters, ray optics and wave optics. Okay, and then last we have modern physics. So let's begin with that, with all the derivations which we can cover from these four chapters. Okay, so first, if I talked about motional EMF, then this is very small derivation. Okay, with a basic concept, that is, see, from the chapter electromagnetic induction, we have understood that the EMF generates due to change in magnetic field, or due to change in flux. Okay, so the flux can change in either ways. Flux has a formula of BA. If the area is changing, if B is changing, if the orientation between B and A is changing, then the flux is changing and EMF can induced, and current can induced. So here the distance, the conductor is changing, and due to which the flux is changing and EMF is induced. So in motional EMF, we have a conductor, let's say rectangular shaped conductor, something like this. Okay, which has one end free to rotate, free to move. Okay, and the magnetic field here is basically present vertically downward or into the plane of the paper. It is something like this. Okay, and the conductor is perpendicular to it. Let's take this loop. It's uniform field. Uniform fields are parallel and equally spaced. Consider this as equally spaced. Don't go with the diagram. Okay, so let's consider this as a conductor PQRS. Okay, in which the current is no current is flowing. It's a simple conductor. Consider a conductor PQRS. Consider a conductor of length PQ, QR, RS, SP, in which three are fixed, PQ, SR, and SP, and you can move RQ. So consider a conductor. Consider the conductors PQ, QR, RS, and SP. Okay, arrange as shown in figure, where only RQ can move in a uniform magnetic field, in a uniform magnetic field B, okay, perpendicular to it. Perpendicular to it. So let's consider this is moving here, okay, with some velocity V. Is moving it with some velocity V. This is the type of technical issues I am facing these days. I don't know why, what's happening. There's no memory issues and stuff, but okay, anyways, let's. Okay, so you can take this length to be X, and this is X, and this to be L. Fine. So now the area of PQRS would be length into breadth, that is L into X. Okay, and the flux linked with it is B into area, and area is Lx. Okay, so due to motion of rod, this rod RQ, okay, of rod RQ, the flux changing because area is changing, because X is changing, and then the EMF is induced. Due to motion of rod RQ, area changes, due to which EMF is induced, and that EMF E is basically given by d phi by dt as per the Faraday's and Lenz law, that is minus d by dt, and your phi is BA, which is BLX, this one, BLX. Now B is fixed, magnetic field is uniform, length of conductor is fixed, it is just dx by dt, that is the rate of change of displacement. So your EMF comes out to be minus BLV, where V is the velocity with which it is moving. Okay, so the negative sign here, negative sign shows basically that the velocity of the conductor is in decreasing direction of X. V is in decreasing direction of X. Okay. So where X is decreasing, V is moving in that way. So it's simply BLV and it's the EMF. And if you want to calculate induced current, then just put an additional variable R, resistance of the conductor. So for the induced current, if R be the resistance of the conductor, then your I induced is basically E induced by R, which is BLV by R in just magnitude. Okay, so this is very simple, but yeah, numericals and concepts could be taken from this topic as well. Okay, So next is self-inductance. So you know from the definition of self-inductance that the change in flux, or the flux basically is proportional to current I. I'm not going deeper into the concepts. I'm just explaining you the basic stuff. And the proportionality constant is Li, where L is my self-inductance. Okay. Is the coefficient of self-inductance. Right? And for EMF, you have minus d phi by dt, that is minus L di by dt. That's the relation between EMF and rate of change of current. Now for the solenoid, we have to calculate its self-inductance. Okay, so consider a solenoid having small n, number of turns per unit length. Number of turns per unit length and current I flowing through it. And current I flowing through it. So basically, the magnetic field inside the solenoid, we have derived in the last video. Magnetic field inside the solenoid B is equals to mu naught N I. Okay. Now we have to calculate the L. So the thing is, we have to calculate its area, then flux BA, and then rate of change of flux. We'll get the EMF, and then we can compare L from there. Or you can simply calculate phi, and you can compare L from here. So the flux phi is also written as BA. So for area, we have to find the area of a solenoid. So what we can do, that let small r be the radius of the solenoid loop. If your solenoid is like this, it has circular loops. So this has a radius r. So area would be pi r square, and flux linked with singleton. Flux linked with single turn would be B into single area. B is mu naught Ni into pi r square. Okay. And flux through n turns of solenoid would be phi is equals to n times of mu naught, and this n can also be written as n by L. If L is the length of the solenoid, I into pi r square, and this term will become mu naught n square pi r square L into I. Okay, so put this as first equation, and as per law, we also know that phi is equals to Li. So you can compare equation 1 and 2. Let's mark it as 2 and 3 because we have already given an equation 1 up. So on comparing equation 2 and 3, L can be written as mu naught n square, area or pi r square, anything, by L. So this is a self-inductance of solenoid. Fine. It's sort of important. The formula is important. Okay, next we can check the energy stored in a inductor. Okay, so next is energy stored in an inductor. So for the energy, we will calculate the work done. We know that EMF due to self-inductance. EMF due to self-inductance E is equals to minus L di by dt. Right? Now the work done, small work done against this EMF would be small work done against this EMF would be in moving small charge. So if it is against, then that small work done should be minus E dot small charge dq. Negative. Why? Because we are talking about against EMF. Fine. So this is dw. Put the value of E here, then it is minus L di by dt into dq, minus plus. So this is L. Put di to be out and dt in like this, dq by dt. And you know that dq by dt is what? Current. So dw is equals to Li di. So total work done would be total work done is the integration of it, which is total work done from, let's say, current 0 to I, Li di. L is a constant that comes out, then I di gives you I square by 2 under limit 0 to I, which is only I. So work done is equals to half L I square. Okay, so the energy stored. So the energy stored in moving it from infinity to some point in an inductor. In moving the charge from infinity to some point in an inductor. So energy stored in moving the charge from some point from infinity to some point in inductor. From infinity to some point in inductor would be U minus U at infinity, which is 0, and it comes out to be half Li square. So the energy which is stored in an inductor is half Li square. Okay, so it's a very simple thing. Okay, so the next is mutual inductance. I think it should be 3. Mutual inductance. Now mutual inductance is between two wires. Okay, the first wire is inducing some EMF on the second wire due to the change in flux linked with the first coil. Okay, so if you talked about mutual inductance of two solenoids, then consider two solenoids. One is this, and let's take other to be this, and the effective length is L here. Small one has a radius of R1 and the other one has a radius of R2. This is has a current of I1, this has a current of I2, and this has N1 number of turns, this has N2 number of turns. So you can write as, consider two solenoids coiled with each other, of length L, each of length L. Okay. R1 and R2 be the radius of two solenoids and the effective area of two solenoid is pi r1 square. Basically, the effective overlapping radius should be taken, which is r1. Okay. And n1 and n2 be the number of turns, and I1 and I2 is the current flowing through solenoid respectively. Flowing through solenoid respectively. Okay. Now we have to calculate mutual inductance. So first we have to calculate the magnetic field. So for the magnetic field, if I am calculating the mutual inductance of first, then I have to calculate the magnetic field of second. So magnetic field due to magnetic field of second coil is B2, which is mu naught Ni. So mu naught N2 by L into I2. Okay, so this is the magnetic field of second coil. Now, this magnetic field, if changing, it generates an EMF in the first coil. This is the mutual inductance. So flux linked with first coil phi is equals to B2 into effective area, which is mu naught N2 I2 by L into, let's take this area, and flux linked due to all the number of turns. This is because of single turn. And flux linked with all the turns, all the N2 turns, N1. So that would be, it is flux in first. Mu naught N2 I2 by L area into N1. And we know the mutual inductance linked with first coil due to second. That is, mutual inductance of first with respect to second is basically equals to phi 1 and I2, because current is in second. That generates a magnetic field in second, and you have to calculate the mutual inductance which develop in first because of the second. So phi 1 is equals to mu naught N1 N2 A I2 and L I2. This will cancel. So the mutual inductance linked with first coil with respect to second is basically mu naught N1 N2 A by L. And the same procedure you can follow for the coil second, the mutual inductance of second coil with respect to first. Mutual inductance linked with mutual inductance of first coil due to second. Okay. Now you can say similarly the magnetic field of first coil. Magnetic field of first coil is B1, which is mu naught N1 I1. Okay. And the flux linked with second coil. Flux linked with second coil phi 2 is equals to mu naught N1 I1 L into effective area due to single turn and due to all the turns. Yeah, due to N2 turns. And due to N2 turns, phi 2 comes out to be mu naught N1 I1 A by L into N2. Okay. And then you have to calculate mutual inductance. Mutual inductance tens of second with respect to first of second due to first is mutual inductance of 2 with respect to 1 is this phi 2 and here it is I1. Okay. So it is mu naught N1 N2 A I1 over L I1. You can cancel I1. So your mutual inductance due to second is also comes out to be same, which is mu naught N1 N2 A by L. So therefore, you can say that the mutual inductance linked with first coil due to second is same as second with respect to first. And this is also known as reciprocity theorem. Okay. So it's a very basic, but it's sort of important. Okay, next we'll move to some derivation of from AC. That is the power laws, reactance, and resonance conditions and stuff. Okay, so next we can do from AC. And first we can check the root mean square current. Okay, current and EMF both have the same method. And here I am discussing about the current, and EMF follows the same method. So basically, the root mean square, matlab RMS value of current, or you can say the effective value of current, is that value of current which produces the same amount of heat. The amount of heat produced by the DC current in a given time is equal to the current produced by this effective value in the same time. Okay, so that effective value is basically your root mean square IRMS value. So if we consider an alternating current I is equals to I naught sine omega t. ठीक है? In a circuit. Now, the small amount of heat produced on passing the current for time dt. For time dt is dH is equals to as per the Joule's law of heating, it's I square RT, I square R dt, and total heat produced in one complete cycle. In one complete cycle, that is from time 0 to capital T. Time 0 to capital T. So that is, this is the heat. It's the total heat, and here it is the integration from 0 say T I square R dt. And this heat is basically equal to the effective value of current. And this is equal to the amount of heat produced by effective value of current. Effective value of current. Okay. That means that heat is also equals to I effective, which is I RMS I square R T. And now you can equate both the terms from equation 1 and 2. Your I effective square R capital T is equals to integration of 0 say T I square R dt. This R and this R will cancel because the resistance is same. Okay. In a circuit having a resistor R, or you can say the resistance of the wire is R. This thing having a resistor wire R. Okay. So now your I effective becomes 1 by T 0 say T I square dt, and that square goes to under root. Then this become square RMS square, then mean, then root. RMS root means square. Now just put the value of I here, which is I naught sin omega t, the alternating value of current. So I effective is equals to 1 by T 0 to T I naught square sin square omega t dt. Okay, so initially I'm solving this term and then 1 by T and under root. So now if I take 0 say T I naught square sin square omega t dt, I can just put the formula of sin square omega t here. The math students know that it's simply the double angle formula, which is 1 minus cos 2 omega t by 2. And dt. Okay. Now you can take I naught square by 2 out, and because they are constant, and we can simply integrate this value. So this become I naught square by 2, 1 become t minus integration of cos omega t is minus sign, so minus minus become plus 2 cos omega t, and 2 omega will go down from limit 0 to capital T. It's very simple. Just put the value here, t plus 1 upon 2 omega. This becomes sine 2, and you can put the value of omega as well, which is 2 pi by capital T and then t. Then minus and the lower limit 0 plus 1 upon 2 omega sine 0 simply. Now you can see here this is t plus sine 2 into 2 pi, that is sine 4 pi, which is also 0. So t plus 0 minus 0 plus 0, and this become I naught square 2 into t. Now just put the value of this to be here and you can get I effective, which is equals to under root 1 by t into I naught square by 2 into t. You can cancel the t, then becomes I naught by root 2. So this is the I RMS value or you can say I effective, which is equals to I naught by root 2. And you can use the same method for EMF also, and it also comes out to be same, E naught by root 2. Okay, so this is the RMS value. And then you have that the average current over the complete cycle is 0. It's very easy, you can simply average out over complete time. And then the peak value relations, they are very easy. And RMS is more important, so I discuss it. If you want, you can comment below for that derivations. And then you have circuits, and for the circuits, for pure resistive, pure capacitive, and pure inductive, it's just a phasor diagram and simple relations. And then you have RL and RC circuit. So all you have to remember is the phasor diagram and the basic conversions of the formula. It's not that big derivation. So next we can learn LCR circuit. We can calculate impedance for LCR circuit, and then the resonance condition. And then I can explain you the power loss in AC circuit, the generalized formula. Okay. So the next is LCR circuit. The chapter is also good for numericals and concept base, so you can focus that portion from this particular chapter. Okay, so for the LCR circuit, we can use the phasor diagram and circuit to determine its impedance. Okay, so for LCR circuit in series, you have three components: inductor, resistor, and a capacitor, which are connected in series. Only series combination is there across a battery. Okay, and you have to calculate the impedance, the phase angle, and everything. So the current is flowing here, and let's say this has a EMF of E is equals to E naught sine omega t, and the current is flowing is I naught sine omega t. Now the potential drop across inductor is VL, which is equals to IXL, where XL is its reactance. Then voltage across resistor is simply IR, and voltage across capacitor is equals to IXC. Okay, so now the total voltage EMF is equals to the sum of all these three terms. And as per the phasor diagram, you can solve this derivation using phasor diagram only if you consider, let's say, this to be my VR. Let's take this as VR, voltage across resistance. Then we know that for the pure resistor, the current is in the phase of potential when the circuit has only resistor. So if VR is along this direction, then the current will follow the same path. Okay, now for inductor, VL leads the current by an angle of 90 degree, and VC lags behind it by an angle of 90 degree. Okay, so in our condition, consider first that VC is less than VL. VC is less, so we can say that as per the diagram, VC and VL are at 180 degree. So the net voltage of VL and VC is simply VL minus VC, because VL is larger than VC. If it is opposite, that VC is greater than VL, then it's VC minus VL. As per the diagram, the net voltage of L and C is VL minus VC simply. And that comes out to be something like this, which is VL minus VC. And you can see that this is VR, this is VL minus VC, and the angle between them is 90 degree. So at the diagonal, you have the net EMF E. Okay, so the net EMF of the circuit is E, which is basically equals to VR plus this VL minus VC. Okay, and if you want to take the magnitude of this EMF, then that is equals to under root of VR square plus VL minus VC का whole square plus 2 into VR into VL minus VC cos 90 degree, because the angle between them is 90 degree. Fine. So this term will goes to 0 and your net EMF comes out to be VR square plus VL minus VC whole square. And if I is the total current, I is the total current in the circuit, then I can write this EMF as I into net impedance of the circuit and VR as I into R whole square, and plus VL can be written as I into XL reactance minus I into XC capacitive reactance whole square. You can take I out from the root and this leaves to R square plus XL minus XC whole square. I and I cancel each other. So the net impedance of the circuit comes out to be what? R square plus XL minus XC whole square. Like this. Okay. Very easy. Now, this is the impedance. Impedance of LCR circuit. You can use the same method to calculate the impedance for LR circuit and CR circuit. But for L, C and R, pure LCR, they have a different method, but it's very easy. They're simple formulas and conversions. Okay. Now you can see the phase difference between this is this phi. So the EMF leads the value of current, and you can write this as instantaneous current of the circuit would be what? I is equals to I naught sine omega t minus phi. Fine. Because here the inductor is dominant. Inductor is bigger than capacitor. Therefore, obviously, the EMF has to lead and current lag behind by some angle of phi. If it is pure inductor, then this phi should be 90 degree. But here you can calculate it. Let's say, okay, if you redraw the diagram, this is my VR. Here it is I. Here we have VL minus VC and your EMF is somewhere here. Right? And this phi angle. Okay. So here you have EMF and the angle between this is phi. Okay. So if you join this line, then this should also be VL minus VC. And as per the geometry, your tan phi is perpendicular upon base. Perpendicular is VL minus VC. And your base is VR. Okay. You can put the values here. VL as IXL minus IXC over IR. You can cut the values of I. Then it become XL minus XC by R. So this is how you can determine the phase angle. Okay. Now, if your VC is greater than VL, then the condition would have changed. The impedance Z would remain same, which is equals to R square plus XC minus XL whole square. This would change. Your I would be I naught sine omega t plus phi. It leads, and your phase angle tan phi would be XC minus XL by R. Okay, and if XL is equals to XC, if both are same, then this becomes the resonance condition. This is the resonance condition. And in the resonance condition, the impedance become R. That means it becomes purely resistive. Both cancel each other, XL and XC. The instantaneous value of I become I is equals to I naught sine omega t. And your tan phi will become 0. That is, there is no phase difference between I and net EMF. And in that case, your XL is also equals to XC. Then your omega L is equals to 1 upon omega C. Then means omega square is equals to 1 by LC. Then the resonance frequency is basically 1 upon under root of LC. It's a very important formula. And you know that omega is equals to 2 pi f, normal frequency. So this frequency will become 1 upon me 2 pi root LC. Okay. So this is what LCR circuit, you get the value of impedance, and then how the current is related. If it is inductive dominant, then there is should be minus phi. If it is capacitive dominant, then there should be plus phi. And if it is purely resistive, then the phi should be 0. Okay. So you can adopt the same method, same things for the other circuit as well, but still you can comment below for any feeds and if you want any other derivation. Okay, the next last is the power loss, the circuit. Power loss in AC circuits, and I will do it for general term. Let's consider EMF of the circuit as E is equals to E naught sine omega t, and the value of current as I is equals to I naught sine omega t minus phi. Let's take this. Now, if they have asked you for capacitive, then you can use plus phi. If they ask for inductive, you can use minus phi. If it is pure inductive, then it's minus pi by 2. If it is pure capacitive, then it's plus pi by 2. It depends on the condition which been asked in the question. So accordingly, you can put, if it is pure resistive, then it's simply I naught sine omega t. As simple as that. So the average power, we can say power lost or dissipated in the circuit, is basically P is equals to E into I, VI. Then that power is equals to E naught sine omega t plus I naught sine omega t minus phi. Okay. Then there is a multiply sign. Then you can get E naught and I naught to be out, and this is sine omega t into sine omega t minus phi. You can divide the equation by 2 and multiply it by 2, and then you can put the formula here of 2 sine A sine B. Okay, so here you can use the formula of 2 sine A sine B, which is equals to cos A minus B minus cos A plus B. Okay, so your P will become power is equals to E naught I naught by 2 cos omega t minus omega t plus phi minus cos omega t plus omega t minus phi. Then the power becomes E naught I naught by 2, cancel each other, cos phi minus cos 2 omega t minus phi. Now you have to calculate the average value for one complete cycle. The average value of power loss for one complete cycle for one complete cycle, that is from T0 to capital T. So if you take the average value of power, then you have to take the average value of this whole term, cos phi minus cos 2 omega t minus phi average. Now this E naught I naught term is a constant, so you can take out from the average, and then it's simply the average of cos phi and the average of cos 2 omega t minus phi. Now here you can see that cos phi is independent of time, so there will be no value of time, so its average will be nothing. So the average of cos phi will gives you simply cos phi, as term is independent of time. Term is independent of time, and if you take the average of cos 2 omega t plus minus phi, then for a complete cycle, you know, the cos and sin is basically 0. If sine have some angle, then 0, and cos with some angle is also 0. Sine square is half, cos square is half for one complete cycle. Okay, so the P average power loss is equals to E naught I naught by 2 cos phi, and that can be written as E naught by root 2 I naught by root 2 cos phi, and E naught by root 2 is ERMS. And that is equals to the average power loss in one complete cycle. And phi is basically a phase angle. So if it is pure capacitive and pure inductive, then phi is 90 degrees, so loss of power is 0. And for resistive, phi is 0 degrees, so the power loss is ERMS into IRMS. So these are some basic and important derivations from this chapter. And apart from that, there are basic relations, very simple derivations, and I think they are more you can use that more for numericals and concept based rather than the direct derivation thing. But anyways, if you have any doubt, you can comment below. I will help you out with those queries in the next video. And for electromagnetic waves, again, there is no such derivation in that. All you have to remember is the spectrum. Just learn the spectrum by heart, the frequencies, the wavelengths, the uses of all the waves, and uh, you should know about displacement current and also the energy density thing, that electric and magnetic field have equal densities. They are also very simple derivations. It's nothing much in that. So, still, if you have any doubts, you can comment below. And yeah. So, thank you for watching this video and do like, share, and subscribe for more such videos.